Okay, so we're going to try to create a new TecPIV project. I'm going to show how to create a new TecPIV project and import DNG files into that project, and correct these DNG files and start the correlation. So first I'm going to start PIV from the shortcut on the desktop, which opens MATLAB automatically. Here it comes. It opens MATLAB going directly at the address where TecPIV is within the folder MATLAB. And then the second thing that the software does is looking at how many workers I can use, so how many computations I can run in parallel. Then we open the main window of TecPIV. So we're going to start with the first thing to do, which is create a new project. So my new project, new. Okay, I'm going to make one on the desktop. I'm going to create a new folder and give it the name of my project. So here, test, select folder. So I have a new folder that's created here. That's called test. I'm going to import experimental frames, DNGs, taking a 10-second interval between images. Import, and I'm going to go get them on my drive. So here into Maxim row, let's look at the experiment 7, for example. We have a bunch of DNG files. I'm going to take just a few of them near the middle so that we have something happening. I open these images. Now the files are created in this folder, so we can see here the structure of our project. It has within the project a folder called row, and in this we have our TIFF files as well as the EXIF metadata associated with the DNG saved as individual text files. Okay, so this is the first selected view of the model. Now we have a player with a selected dataset. We have only one dataset at the moment, so it's the raw images. And we see that this view of the model are oblique, so we're going to need to correct that. To do that, I'm going to import a calibration frame. Calibration frame is also a DNG file. The time increment doesn't matter. I'm going to go back to the same row, and in my original dataset I have two views of a calibration board, but I only need one here. So I'm going to take the second one, open, alright, so this is the view of the calibration board. So now we're going to count how many control points we have on this calibration board and tell the software what's the size of the squares. So I'm going to the next menu, calibration, extract control point, and I'm going to tell the system, I think this is 30 and 28 points, and the squares are 15 millimeters by 15 millimeters, and the physical units are millimeters. So now we start. I'm going to click the 4 corners of my calibration board. There, there, and there. Now I verify that my red crosses are at the corners of my control points, and it's all good, so I can tell now the system to rectify this image. We're going to use a method with projective and polynomial to correct for the linear and non-linear distortions. That's the position of the points and where we want to send them. This is the movement of the points. we use the resolution of the image in the center to calculate where to send the point. Now we're going to check our projective transformation, see how good a job we have done. So I'm going to click my 4 corners again, so we can verify if the points line up with where they should go to. And now we gonna start the second part, which is the non-linear, but in between we can go back to our MATLAB window, and it tells us at the end of the linear projection we had an error of 13 and 14 pixels along the x and y axis. So that's quite significant. So there is some non-linear distortion that we need to remove. Also tells us that the resolution of the image in the center is 6.7 pixels per millimeter, and that's going to be the resolution of our image at the end. Okay, so now we've applied a non-linear transformation with the polynomial function of degree 3, and therefore our images, the edges are not straight anymore. Okay, we see that we have a lot of deformation at the edges, but in the center we now have something that looks a lot more regular. We're going to verify. Again, we have found all the points, and now we can crop our image because there's a lot of distorted image that we don't want to use, since the calibration is only this area. I'm going to create a mask and crop. So this is our image now. It has a much more regular grid. And now what we can do once we have finished the calibration is apply this transformation to our dataset. So I'm going to use pre-processing, undeformed dataset. I'm not going to rotate these images about a vertical axis. I'm going to leave them as they are. And now we start. So I'm using 4 computation cores simultaneously to rectify this. Each core will be rectifying one image to test. In the folder calibration, original image, and now a folder called rectified, which contains a rectified image of the calibration point. It also contains all the figures that we have created during the rectification. Now in the test row we have a new folder called rectified, where we are finding the images of our model during the deformation, but now these images have been rectified and cropped. It's almost done. Alright, so this is our image. Now, before we do the correlation, we can adjust the contrast on this image. We want to use this distribution of particles at the surface of the model to identify each image sub area and see how much it moved. So we're going to adjust the contrast to see these particles even better. So I'm going to inverse this image, subtract the background, using a Gaussian curve with the parameter 50 and 10. Now we start. This is what we obtain, and that is good enough to calculate the vectors in the center in this area. So next menu is processing. This is when we do the correlation, PIV. Okay, so we're gonna use the dataset rectified. We're gonna use a single pass with a window of 128 with a grid size, final grid size of 32, we're not going to do this. We're going to leave the universal outlier and interpolate. And I'm going to check how many images. I have 6 images. We're going to adjust the contrast before we do the correlation, and we're going to use a region of interest. We're not going to calculate the vectors everywhere. We're not going to deform this region of interest here. Okay, now we're going to define our region of interest. We're going to calculate between here and here, where we have sufficient number of points. And now we start calculating. 2,420 vectors per image pair, and it's going to be done quite rapidly. So this is what we obtain. We can then play with what we display. We have the displacement shown as the vectors here. We have a vector derivative behind and the deformed model. So display settings. We can change how many vectors we have. We can have every 2, apply, more, maybe too many now. So 4 was a good setting. We can show the derivative here, yx, and we can interpolate the derivative. That's showing us where the shearing occurs along this edge of the model. Nearly nothing is happening on the other side. Now we can change the color scale. We have almost nothing positive, nothing negative, so we can change to a color scale between white and blue, for example. Apply. Alright, so here it shows, but we still have our 0. That's not exactly at 0. Display setting. We're going to display an arbitrary range between a minimum of 0 and a maximum of 0.005. Alright, so now we have a good control of our color scale that displays where the shearing is happening. We see our vectors nicely. We have a scale for these vectors. What we can do as well is change the image number. So this is image number 2 in our series. If we call number 3, okay, we have slightly different vectors. And number 6, at time 40, we see that now our vectors are a little bit more straight and also a little bit longer. I think there was an error. The images were taken at 5 second time interval, so the vectors here, the magnitude is wrong. Another thing that we want to see is that this image now has a physical scale, so we still have the dimension in pixel along the x and y axis, but we also have a scale bar telling us what that corresponds to in physical units. So we can really try to analyze the deformation in this model using the calculated displacement and see where strain is accommodated. And then to close the project and be able to reopen, we're gonna save and close instead of using the big red arrow. Save and close. We're gonna save all the figures associated with this project so we can reopen it to continue where we left it, for example to export some of these images. So we're back into the main TecPIV folder. Project is closed, so I can go to TecPIV, open, If I open, I just see what it is. I want to run it. So we are starting a new parallel pool. In the meantime, we can see what we have in the project folder. Now in the folder rectified, we still have our corrected images here, but we also have a new folder called vectors. And in vectors we have a number of vector fields. Alright, so now we have reopened. We don't have any project, so project, open, go to the desktop, test, and I select test, open. And we reopen just where we left, even at the same image number, so it's all working well. Display, export this frame. Oh, there's an error. Okay, we're gonna save and close.